Okay. Welcome everyone. Welcome to Quantum Matter in Math Physics series. And today we have a very special guest, Professor Mirjam Cvetic. I hope I pronounced correctly. The topic today will be about F-theory, and there will be two talks on Wednesday today and Thursday tomorrow. So today is part one about construction of particle physics models. Also, let's welcome Mirjam for the lecture.
Yeah. I may not pronounce your name correctly. Is it Juven or is it Juven?
Juven, fine. Yeah, Juven. Yeah.
Yeah. So thank you for your kind invitation. It's really a great honor to present an overview of the work on F-theory compactification at this quantum matter string theory seminar series. So as you mentioned, my talk will be part one talk that will focus more on physics aspects of constructions of particle physics models in F-theory compactification. And tomorrow, Ling Lin will continue with F-theory part two, highlighting more formal mathematical aspects of this program. So as I said, this is a broad program where one is developing mathematical techniques to construct globally consistent F-theory compactifications that would have properties of the particle physics models, in particular the gate symmetry and the matter spectrum of the standard model in particular. So these techniques developed studies of elliptically fibered Calabi-Yau fourfolds and address the nature of its geometry in order to deduce both the gate symmetry group, the matter spectrum, as well as other global gate symmetry constraints that in more recent years have become more prominent. So I have to apologize when I'm going to overview some of those things. I will emphasize primarily things done at Penn. The main part of this talk will actually describe the status of particle physics constructions where one uses toric geometry techniques, which are very well suited to get the right data about the gate symmetry and matter spectrum. And focus will be, as I said, on the standard model constructions, in particularly directly getting standard models with three families of quark and leptons, which was initiated a few years ago. But the highlight will be really the landscape, the whole broad study of such consistent three family standard models that was actually developed only last year. And in the last part of my talk, I would also like to highlight some further analysis in the studies, more advanced and technical. In particular, an important issue in physics consideration of this construction is to address the properties and constraints that we could have for moduli stabilization of these compactifications. That is quite a recent work from this April. And then in the last part, I will highlight some progress we have made toward computations of the number of charge vector meta pairs, namely getting the information also on the vector pairs would give us at the end the full information on the massless matter spectrum in these compactifications. So those would be the last three works will be basically the key things of most recent developments that I'm going to overview. So the outline of my talk will go in similarly in three stages. First, I'll just outline some features of the F-theory constructions and focus on geometric approaches. in particular focusing on the origin of non-abelian gate symmetry, the appearance of matter, and also the Yukawa couplings about among matter candidates. In this more overview part, I will also highlight some of the developments that actually took place among physics community, which is for studying not only non-abelian gate symmetries, but also abelian gate symmetries, both continuous and discrete ones. And I would like to also delegate more formal aspects of discussions of geometric origin of this gate symmetries in F-theory to Linglin's lecture tomorrow. Then I'll turn to constructions of particle physics models, namely key building blocks that we need to obtain globally consistent models, and I will focus on applying these constructions for toric spaces where algebraic geometry techniques are well developed, and then highlight really the whole landscape analysis of these three family standard models. And in the last part again, I'll go to moduli stabilization results, namely focusing on how moduli stabilization scenarios apply to this big class of three family standard models, and also some progress toward full matter spectrum calculation, which unfortunately has not been done in these classes of standard models yet. And I'll conclude with some work in progress and open issues. So what is F-theory? One way of getting to the formulation of F-theory is to start with the type 2 string theory that includes D branes. In particular, in this context, we'll focus on D7 branes, which in the weakly coupled regime are described as boundaries of open strings. And we have conformal field theory techniques to address the properties of weakly coupled type 2 string theory. However, if we want to get to a strongly coupled regime, namely when the string coupling is not set to be small, the D branes become gravitational objects. They back react on this Calabi-Yau space on which we compactify them and turn the Calabi-Yau space non-Calabi-Yau, namely they become just killer spaces due to this big back reaction. So we are now in the geometric phase of compactification, where we can now describe this strongly coupled regime of type 2 string theory as now this back reacted non-Calabi-Yau space, to which we add two extra dimensions that explicitly parameterize complexified string coupling of the theory. So the compactification itself now becomes a 8-dimensional space, where the original 6-dimensional space is now, we add to it an extra torus that, that we fiber over this 6-dimensional space that parameterizes this explicitly the strength of complexified string coupling. And so we view that now as compactification of a theory on torus fibered Calabi-Yau fourfold, namely 8 real dimensional space. Now, through chain of dualities, and in particular, one is quite important, is the duality of this F-theory description when compactified on a circle and taken to the so-called Coulomb phase. This theory becomes equivalent to description of M-theory or 11-dimensional supergravity on the same torus fiber Calabi-Yau space. And of course, we have a chain of other dualities that then relate us back to type 2 theory, but there are other setups that relate F-theory also to heterotic string theory, both E8 cross E8 and SO32. But again, our main focus will be really now on the F theory only. So basic ingredients of F theory compactification, we would take the road that came now from this type 2B perspective. And so, as I argued, we are adding a torus whose modular parameter, namely of torus, the elliptic curve, parameterizes the complexified string coupling, and it has, due to nature of torus, manifest SL2Z invariance, namely non-perturbative S-duality invariance of type 2B string theory. So we take this torus over a three-dimensional back-reacted Hilbert space, and we fiber it over the space. So the full-fledged geometry that we are describing is now a torus fiber Calabi-Yau space that turns out actually at the end to be singular. And the fact that this Calabi-Yau is key to describing this compactification four-dimensional theory with n=1 supersymmetry. So one way to describe this fibration of a torus over this base is via Weierstrass normal form, which is describing this elliptic curve as hyperplane constrained in a certain weighted projective space, namely two-dimensional complex projective space with weights, so CP2 with weights of complex coordinates to be related by weights 1, 2, 3. Okay. So in particular, both these coordinates of this elliptic curve now, as well as coefficients F and G, when fibered over this base, okay, become certain sections, namely specific holomorphic functions of this base coordinates. Okay. In particular, F and G become sections of anti-canonical bundles on this base B of degree 6 and 4 respectively. This conditions actually ensure that this whole construction of the Calabi-Yau manifold is indeed Calabi-Yau. It has its first term class equals 0. Now from now on, all the dimensions will be complex, okay? So eight-dimensional Calabi-Yau manifold is really Calabi-Yau fourfold. The base is 3 complex dimensional. Any other codimension objects will be all in complex codimensions. Are there any questions? Okay, let me continue. Am I too slow? So let's continue discussing the physics of appearance of gate symmetries in this F theory compactifications. Okay, so in particular, this vibration, torus vibration that keeps explicit track of the strength of the complexified string coupling, okay, has to become typically singular at certain loci in the base, just to ensure the fact that this remains Calabi-Yau manifold. So in particular, if we focus on a locus in codimension 1 in the base, namely a divisor, this torus could degenerate over this divisor, become singular. And what it really signifies is location of the D-brane, back-reacting D-brane, actually completely non-perturbative, so-called PQ D-brane. The appearance of these codimension 1 singularities signifies the appearance of gate symmetries. So let me turn and say a few more words about the nature of the singularities and how they signify the appearance of non-abelian gate symmetries. Well, the reason I want to do that is I want to, at the end, construct standard model. And of course, standard model does have non-abelian gauge group factors, SU2 and SU3. So when we look at the elliptic fibration along the locus of, along this divisor S, this elliptic fibration described here in this Weierstrass form degenerates, becomes singular, and the order of singularity, both of F and G coefficients, as well as its discriminant, specifies the type of singularity we have encountered. These singularities, of course, have been analyzed by mathematicians, okay, and they go under the Kodaira classification. Okay. Now, what we typically do now, to deduce the nature of the singularity, we resolve it. So we resolve this singularity in the fiber, okay, via trees of CP1s, and the nature of those trees specify the particular type of resolved fiber. So here I'm pointing out like I5 fiber that involves 5 P1s connected in the specific manner. And it turns out that all these resolved fibers are in one-to-one correspondence with the corresponding Dynkin diagram. And here, for example, IN fibers are associated with SUN gauge symmetry. And here I am denoting SU5 example. Okay. So how does this gauge symmetry appear from the nature of this resolved singularity? So the way we connect this geometry to physics is we Poincaré dualize all those resolved PIs into 1,1 forums on resolved Calabi-Yau fourfold. Okay. It's this Poincaré dual 1,1 forums. Then when combined with the C3 potential that is borrowed from F-theory, M-theory duality, okay, expand the C3 potential in terms of this 1,1 form, produces for us in Kaluza-Klein reduced version AI gauge bosons, which are Cartan massless gauge bosons in 4-dimensional compactified theory. So the lesson is from each of those PI, there is a 1,1 forum that supports Cartan gauge boson of the corresponding non-abelian gauge symmetry. Okay. The way non-abelian gauge bosons are obtained is really, again, borrowing from M theory and taking two branes from N theory that now wrap those P1s in specific ways and actually generate through this M theory connection, Kaluza-Klein reduction, non-abelian gauge bosons in the theory. So this is the nature of non-abelian gauge symmetries. I should mention that the abelian gauge symmetries are different, and I'll turn to them later. Now, when two divisors intersect in the base, we also get a singular vibration. And we associate the appearance of matter with these co-dimension two singularities. So again, in the standard model, we have quarks, which are in bifundamental, say, bifundamental representation of this non-abelian gauge group factor SU2 and SU3. So typically we proceed with in a similar way by taking the singular fiber at co-dimension 2 intersection, we resolve it, and generically we get I2 fiber at this co-dimension 2 loci, and then again we invoke M theory, F theory duality, and wrap parts of this I2 fiber with M2 meta curves, which signifies now the appearance of matter that is actually charged under corresponding non-abelian gauge symmetry. And we use determine the actual representation of this matter for each case using intersection theory. So this is matter. I should say that actually to get chiral matter, not just vector pair matter, we have to introduce not just geometry, but also gain G4 flux, which is a field strength of the C3 flux borrowed from M-theory, F-theory duality. And it's this G4 flux that has to be judiciously turned on in this compactification to get chiral matter. So F-theory is not all geometry, it has also non-trivial four-form fluxes. And when three divisors intersect, we can identify Yukawa couplings. And at the end, one would also like to determine the magnitude of these Yukawa couplings. But in this talk, I will not be able to say much more about that. Okay. So that was non-abelian gauge symmetry and matter. Now, how about abelian gauge symmetries, in particular U1s? Well, you know, standard model does have U1 hypercharge. So to understand the construction of U1 gauge symmetry, one has to be, realizes that the geometric origin of U1 gauge symmetry is different from the non-abelian gauge symmetry. In particular, what we need is to have just U1 gauge bosons. They have to be supported by 1,1 forms that would be dual to isolated I1 type fibers. And so the main insight into origin of abelian gauge symmetry is that actually the number of that type of 1,1 forms is in one-to-one correspondence with the rational sections of elliptic fibration. So how does the appearance indeed of this isolated 1,1 form relate to appearance of rational sections in elliptic fibrations? Well, let's look first at the elliptic curve and the appearance of rational points of elliptic curve, which are associated with the so-called Mordell-Weil group of rational points. Okay. So we have a elliptic curve. In the Weierstrass form, it has a distinct point, the so-called 0 point, P. And now we are looking for solutions for rational points of this elliptic curve defined in field K by a Weierstrass form. Okay. So finding such rational solutions would produce additional rational points on this elliptic curve. These points, rational points, form a group under addition, namely the so-called Mordell-Weil group of rational points. So having an additional rational point on elliptic curve, now that when we do elliptic fibration, this rational points induces rational sections, which can then be organized together as we go over this fibration, with this vibration over the base into second well-defined copy of the related to the base divisor. Okay, so those induced rational sections produce for us a second copy of related to the base of this Calabi-Yau fourfold. Okay, and this new copy can be viewed as a new divisor in the Calabi-Yau fourfold. It is again co-dimension 1, right? But it's not what we call vertical in the case of non-abelian gauge symmetries, but the so-called horizontal divisor. And per se, it's completely non-singular, unlike vertical divisors. Okay? So from this divisor via Poincare duality, one can then construct 1,1 forum, which then supports the U1 gauge field in the theory. Now it turns out that the key features of these horizontal divisors are specified via so-called Chiuda map, okay, which actually defines this divisor as orthogonal to the base divisor associated with the base, as well as specific a combination of the Cartan divisors of non-abelian gauge symmetries, namely those associated with these P1s in blow-ups of codimension 1 singularities for non-abelian gauge symmetries. So those are Cartan divisors that have to be combined together to define proper horizontal divisor that supports physical U1 gauge field. This coefficient Li are again geometric, associated with intersections of these Cartan divisors. And it turns out that this combination has important implication for further determining the full global gauge group structure in the presence of U1 gauge symmetries and non-abelian gauge symmetries, and have some implication for swampland. And I hope that Ling will say some more about this consequences. I will only apply them to the standard model. Okay, now this is very brief sort of a comment on the work that was quite extensive in the past 5 years to 8 years, where among physics community, one was constructing explicit toroidal elliptic fibrations with additional rational sections. This is well understood in math community, and this construction of additional rational sections actually reduced to studies of line bundle constructions on elliptic curves, which are typically written as Calabi-Yau folds, namely hyperplane type constraints in blow-ups of weighted projective spaces. So for example, if we have just the special zero, just the section, this is the standard construct Weierstrass construction, actually now written in Tate forum, no additional U1. When we have an additional section, this resulted in Calabi-Yau in a blow up of certain weighted projective space with blow up at one exceptional point. And then our group at Penn focused on constructions of elliptic fibrations with 2 additional rational sections, namely producing 2 additional U1s. First, as a generic Calabi-Yau in DP2, but then later on also led to constructions of non-generic cubic constraints in P2 themselves, where one could explicitly study collisions of these rational points. And that actually led to now when those rational points collide, this leads now when to enhancement of gauge symmetry. The original abelian gauge symmetry gets enhanced into non-abelian gauge symmetry, namely these horizontal divisors turn into vertical divisors, and one can trace these gauge enhancements very explicitly in geometry. And also that led to constructions of new type, higher index meta representations of non-abelian gauge symmetry groups that appear when those rational points collide. Higher N constructions, we've done some specific work with 3 additional, but going beyond in systematic study of how to construct such elliptic fibrations, it's really at this point unclear. So I don't have much time to go into that. This is just a side comment, but I think again, I would direct you to Tassi review on abelian gauge symmetries that was written together with Ling. So along this line of Mordell-Weil group, I should mention that the Mordell-Weil group of rational section that supports U1 gate symmetry also has another part, the torsional sections. So namely sections that when we add them up and time, they become rational sections. And these torsional sections are associated with trivial Shioda map, but nevertheless, this triviality has impact for enhancement of non-abelian gate symmetry, namely due to this rational coefficient of associated with the Cartan divisor of non-abelian gate symmetry in the Shioda map. It turns out that the global structure of the resulting non-abelian gate symmetry in the present of torsional section is non-trivial. The original Lie algebra of non-abelian symmetry gets modified out precisely by the order of this torsional sections. And our group also pursued some of the studies when we studied with the rational section and we turned it through deformation into torsional sections that led to further gauge group enhancement. And we were actually, after addressing higher index representations now for this new gauge group, new globally defined gauge group enhancements. But again, I don't have much time about that. But and this,
can I ask a quick question about this?
Yes.
Is there like I guess there's an upper bound on the MK, the values of the MK that we can have? What is
yes.
it like?
Well, it may have to do, you see, this K is encoded in the actual fractional integers with which, you know, the Cartan divisors of non-abelian gate symmetry enter the Shioda map. I don't have the answer. What is the upper bound?
Okay. But do you know if it's like, I don't know, it's order 10, order 100?
I don't think we encountered examples like that. You know, it's the bigger the SUN maybe, but then again, we have limits on gauge groups.
Okay.
Maybe, yeah. I don't have a key answer to that. Examples, of course, that we studied were always lower, right? Lower AN singularities, and so that led us typically only to Z2 and Z3 or direct products of that type. Okay, I think I said I don't have an answer. There is a chance that it would be, you know, there could be a bound on that as well, and it's an interesting question. Similarly, as a bound on the number of rational sections in elliptic fibrations, you know, in globally defined Calabi-Yau fourfolds. For example, it's an important question because it would give you an answer about the compactifications with maximum number of abelian continuous U1 factors. So
Thank
these
you.
are open questions, and I don't have definite answers to that. But
so,
very yes.
Again, Mirjam, can I just
Yeah, I actually was thinking maybe that Link could chime in too.
Yeah, for the torsion part, at least it's known that NK, as written on the notes here, can be at maximum 8.
Can be at maximum 8. Okay, that's good. Okay,
yes.
Thanks.
Yeah.
Okay.
Thanks.
Well, thank you, Ling. Yeah, so you at least clarify this. When you have the multiple factors, right, the story is not completely clear, right?
So from the geometry, I think the limitations are that you can have a maximum in the at least in the pure torsion part, only 2 factors. And the maximum value there is NK equals 4, if I remember correctly. So you can go up to Z4 times Z4 in terms of model torsion.
Okay. So that was classified in the math community, I would assume, or yeah?
Yes.
Yeah, of course. Thank you. Yeah, thank you. And that's actually quite relevant also for things that you will have to say tomorrow, right? So indeed, and examples
right,
that.
Indeed, yeah.
Yeah,
Yeah, I will comment on this tomorrow, hopefully a bit more clear.
So so I hope that clarified some of the points on that. Okay. All right. So last thing, very briefly, I would like to mention also the appearance of abelian discrete gate symmetries in particular, for some of the standard model phenomenology, one would like to introduce also discrete, for example, Z2R parity symmetry that could prevent certain baryon number violating couplings directly in the standard model. So it's of real interest as well. And that study of discrete symmetries, gate abelian symmetries, is associated now with the fibrations that do not admit a section, but a multi-section. Namely, for Z2, you know, if you do double cover of this example, you would really get a section. But by itself, the construction is built out of multi-sections, and this would be like sort of a picture description of bisection example in this a torus fibration. Okay. So the claim is that appearance of bisections produces discrete ZN gate symmetry, and that has earlier work on that already, but this drew a lot of attention in mid 2015s. And I should say that our group also contributed to this by actually constructing explicitly the standard model that has this bisection that acts indeed as R parity in it. Just maybe some connections of, yes?
May I make sure? When you say Z2 R parity, is that the same as a Z2 fermion parity that acts on all the fermions with -1?
Yes, it is related to that. Yes, it is related. This gate symmetry you can assign to each of the fermions a specific, matter parity. And it turns out that actually this construction produces exactly the correct matter parity that has no anomalies.
And that Z2 will be gauged.
Yes, effectively it's gauged, yeah. Because here it does come. This, I want to argue that actually the symmetry is gauged in F-theory compactification. So let me point out how we sort of understand the connection of appearance of discrete gate symmetries from U1 continuous gate symmetry. So we had the original construction, right, where we had a section. Okay, independent. So we have, I'm showing an example when I have 0 section and the corresponding additional section. So this is a construction with U1 gate symmetry. And then it's certain codimension 2, this fibration degenerates into I2 fiber. Okay, that, so the one of the P1, right, collapses here. And then we can now deal by filling into this collapse P1 an S3, namely performing in this case a deformation into completely regular torus, but now at the expense of this collapse 0 and additional section, they become now in these constructions really a bisection, form a bisection together. So the symmetry that was originally U1, it's claimed to be Z2, but one sees that also in the field theory interpretation, because at this codimension 2 a singularity, there is a matter appearing, and you can determine the massless matter field, say, would have a charge 2 under U1. And now this geometric deformation to bisection geometry is now viewed as phi field acquiring vacuum expectation value, namely breaking U1 symmetry down to Z2 because of its charge being 2. So this is a quite nice interpretation of transitions between continuous and discrete abelian gate symmetries and the corresponding field theory that happens at the level of the spectrum of the theory. Last but not least, it is quite intriguing as it turns out that these geometries with n sections are related to Tate-Shafarevich groups of order n, and this relationship was actually explicitly demonstrated for Z2 case first, and it took a bit longer to do it for Z3 case because the actual action of the HFRA group in the case of Z3 is non-trivial. How much time do I have? Because I seem to be going very slow, so.
You have at least 45 minutes.
Okay, all right, so let me go on, because I really want to come. I spend a lot of time being a little slow, but at least I hope I gave you some glimpse of where we stand on these different building blocks in the construction. I have a slide for the HFRA Ridge group for Z3, how it acts non-trivially with 3 group elements, even though the actual geometry has only Jacobian and a single trisection. But this is just as a side comment of more formal interest. And now that brings me to the key part of my talk, which is construction of particle physics models. And I'm going to apply these techniques that I was spelling out for the case of weighted projective spaces. Okay? So as a starting point, we have to find the appropriate elliptic curve that would have the right properties for us. And so the examples I'm going to take would be hypersurface constraints in 2-dimensional toric varieties. So those are generalized weighted projective spaces whose data is encoded in the corresponding reflexive polytopes. And there are 16 of them. So this will define Calabi-Yau one-fold, the elliptic curve, the hyperplane constraint in this weighted projective space. Now we have to fiber this elliptic curve over a base, 3-dimensional base, and ensure that this fibration produces elliptically fiber Calabi-Yau fourfolds. So both coefficients of the hyperplane constraint as well as coordinates of the weighted projective space become specific sections. They become really holomorphic functions, sections of specific line bundles of this base. And for this toric polytopes, it turns out that this fibration that determines the type of sections that this fibration defines is defined only in terms of anti-canonical divisor of the base and it turns out 2 additional divisor classes. So it's this choosing elliptic curves really as hyperplane constraints in 2-dimensional toric spaces gives us very specific features of this fibration. So I'm choosing that because we can be very explicit now, and also because we get really intriguing particle physics out of it. Okay, so there's one thing I was still missing, which was how to determine the chiral index of the matter spectrum, namely to make sure that we have a chiral number of particles, matter particles. As we all know, standard model is determined by 3 families of quarks and leptons, so they have chiral index 3. So the way we achieve that, we have to add 4-forum flux that we integrate now over the matter surface, right? Namely, that's where the matter appears, okay? And it turns out that this 4-forum flux is chosen to be in the 4th cohomology of this Calabi-Yau fourfold, and actually has to be in the so-called middle fourfold cohomology in order not to contribute directly to other superpotential terms, which at the end, other types of G4 flux would be relevant for modular stabilization. But for chirality, it's only this middle cohomology flux. And one has developed really geometric techniques to determine both the basis of this G4 flux as well as the geometry of matter surfaces, by which we determine at the end the total chirality. this is not now the end of the story. The complication comes in this construction due to appearance of this four-forum flux. Namely, this flux sources other other branes. In particular, it sources D3 branes, and the total flux from them cannot escape the compactified space. This is one way of saying Gauss's law has to be satisfied, and none of this flux can escape the compactified space. And thus the flux contribution now and the number of D3 branes have to add up to specific topological number, which is the Euler number of the Calabi-Yau fourfold. Okay. This is an important constraint, and it goes beyond geometry, like chirality goes beyond geometry. And it also, furthermore, it has to be satisfied for positive and integer number of D3 branes. And that puts additional constraints, which are globally consistent compactification. And also in other types of compactification, that was always the hardest constraint to satisfy for global consistency of these compactifications. And then there is furthermore a non-trivial constraint on the integer values of the four-forum fluxes. So implementing all these constraints, okay, we want to now construct globally consistent models. And as I keep saying, I'm going to focus on the standard model. And this is the one that emerges naturally from the choice of F11 polytope. So this is the two-dimensional space P2 with 4 non-generic blowups. Okay. Now the elliptic curve in this F11 space is determined by the hyperplane constraint, where now F11 coordinates are here, but also the coefficients S1 through S9. Okay. Now, so this would be elliptic curve that we construct in this context, and now we have to construct the full-fledged Calabi-Yau space, and that, of course, puts now constraints on coordinates and coefficients Si, which are now sections of specific line bundles of the base, and that is actually explicit result for the coordinates of the F11. Namely, they are sections of this line bundles, and sections have to be sections S1, right? These coefficients are sections of line bundles of that type. So what we can see is, as I said earlier, it turns out that both this nature of the sections depends only on hyperplane divisor classes and anti-canonical divisor classes, right? As well as S7 and S9 divisor. Everything can be expressed just in terms of S7 and S9 furthermore. Anyway, what one observes is that this fibration, this Calabi-Yau fourfold at locus S3 equals 0, it degenerates precisely to I2 fiber and signifies generically appearance of SU2 gate symmetry. At S9, 0 locus, we obtain I3 fiber, appearance of SU3 gate symmetries. And those are the actual corresponding Cartan divisors. And now we also have, of course, it's elliptic fibration. We have 2 rational sections here. This is the 0 rational section, which we get from this particular intersection. And then we find one more rational section, and that's the one that signifies the appearance of an additional U1 that we need. Okay, so we did get, as far as gate symmetry goes, the standard model gate symmetry. There is more to the story, because the appearance of U1, as I was alluding to, indicates also new global constraint on this gauge algebra. And the way one can deduce this additional global constraint is looking at the Shioda map associated with this U1. And we see that the Cartan divisor have these rational coefficients, right? And they turn out to produce now an additional non-trivial center of order 6 for this gauge algebra, and thus the corresponding global symmetry deduced completely geometrically for this construction is actually SU3 cross SU2 cross U1 mod Z6. Now we crank on the technology to determine the representation of matter fields. And again, we obtain the spectrum of left-handed quark, the left-handed leptons, and so on, with the charges and representation that is indeed compatible with this geometric derivation of the global gauge symmetry. Now this is not the end, this is geometry now. Now we have to go to flux, and that is more involved. The construction of this middle cohomology G4 fluxes also induces the now chirality for matter, but also we have to satisfy the tadpole constraints. So in early days, we just took a simple example of this fibration where we took the base to be just P3. There was not much freedom in choice of divisors. There was hyperplane divisor, and all this S7 and S9 are basically determined in integer multiples of hyperplane divisors. And we turned on flux. We then, middle cohomology flux, we checked for each of these constructions that allows us to produce Calabi-Yau fourfold, how many integer values for D3 branes we have and how many families we have. And first of all, you know, the allowed Calabi-Yau spaces are there only for finite number of integer numbers, so that we satisfy the section condition, and then turning on the flux produces for us for tadpole cancellation the number of D3 branes and number of families. And so you see, we have examples for these classes where we have no solutions for tadpoles, but we have solutions that satisfy tadpoles, namely positive integer values of D3 branes, and also chirality is fixed, it's all correlated. And surprisingly enough, those two things pop out, a special example. So that looked very easy, because what we have now is really standard model with just 3 families of quarks and leptons and nothing else in the D7 sector. We do have gauge sector associated with this 46 or 64 D3 branes, but prior to moduli stabilization, we can shove this away from the gauge sector associated with the standard model. So, but there is additional sector there, but it could be made really dark. And the key thing is just 3 chiral families of quarks and lepton and just standard model gauge group, which is quite intriguing because there are no chiral exotics or none of these extra things that one often gets typical in constructions. So this is easy, and the natural question that comes about, okay, is that just tip of the iceberg? Yeah, I said that 5 years ago, and yes, indeed, it is just the tip of the iceberg. And so finally, this is the focal part of my talk, which is now really trying to explore this whole landscape, landscape of just standard models with just 3 families of quarks and leptons in this broader context of toric analysis, namely by not just choosing the simple base, but really scanning all the allowed toric bases for which we can construct consistent 3-family standard models, right? So this is the landscape analysis with some intriguing new byproducts. In particular, I said, here we are, we have taken this elliptic fibration that generically produce for us the right gauge symmetry group. But now we will take a base that is associated with the general 3D reflexive polytope, not just P3, but also other constructions. There are around 4,000 of them in 3 dimensions. And so their data is encoded really in the so-called fine star regular triangulations of chosen polytopes. So each polytope has many different triangulations, which at the end determine actually different intersections of divisors in those spaces. So they are different compactifications. And of course, the more complex the polytope, the triangulation grows exponentially with the complexity. So there is huge number of possible bases now. Now we will take the next step and choose the divisor in those bases. And now I'm making intriguing special choice. I'm going to choose these divisors S7 and S9. Those are the only ones that are still free beyond anti-canonical divisor. And I'm going to choose it to be anti-canonical divisor, which is particular choice. But the consequence of this choice is that both SU3 and SU2 divisors specified by S9 and S3 equals 0 locus are also in the anti-canonical class. So the size of the gauge coupling associated with SU3 and SU2 gauge group is related precisely to the volume of these divisor classes, which are anti-canonical classes. So the magnitude of gauge coupling both for SU3 and SU2 is the same. And what's even more intriguing, there is more involved calculation to determine the size of the divisor for U1 via so-called height pairing procedure. And it turns out that for this divisor, the volume is 5/6 of the anti-canonical divisor class volume. And the corresponding gauge coupling with proper normalizations turns out to be, again, related to the volume of anti-canonical divisor. And these numbers that are geometric precisely ensure that we have a standard model where the couplings are related in this specific way, which is a famous gauge coupling unification relation. So this choice of anti-canonical S7 and S9 to be anti-canonical divisor really takes us in a constructions of standard models that by construction have gauge coupling unification. And that's quite intriguing on its own, okay? Now, as we deform this construction, we could see that these models, geometrically enhance to Patti-Salah models, at least within the historic construction. But in particular, Taylor and Turner analyzed the structure of fibrations with a standard model gauge group, and they deduced, first of all, that this is, if you want to stick just to the standard model and standard representation, this construction is unique. And furthermore, they saw that there could be enhancement to gut symmetry group, but this is outside the domain of the historic deformation. So that's the one we couldn't see. Nevertheless, it's rewarding that, this analysis actually is bigger in scope. And as a byproduct also produces the gauge coupling unification. Now the hard part is to ensure that we turn on the G4 fluxes that ensure 3 families of quarks and leptons, and also of course the 3 tadpole constraint. Okay. And now constructions of this G4 fluxes for this particular case can be also put in a more geometric domain by constructing them in a basis of a product of 1,1 form that are Poincare dual to divisor classes. So it's quite geometric way of constructing possible middle cohomology G4 fluxes, and then ensuring that these fluxes would give us also no tadpoles. So chirality, D3 tadpole, as well as integrality of G4s have been all now cast with turning on of this G4 fluxes in terms of intersection number of specific divisors in the base. So it's really has been reduced to geometrical conditions. It's quite technical, but the outcome is really intriguing that all this data at the end becomes expressed in terms of intersection number of divisors in the base. For the special case when these divisors S7, S9 are anti-canonical and choosing number of families to be n sub f, the tadpole conditions really take this geometric form, namely the number of D3 branes has to be integer positive value and is related to triple intersections of these anti-canonical divisors and the choice number of families. Okay. So I would say that in some way we have geometrized in this context the tadpole cancellation, and even more intriguingly, since triple intersection is property of the whole polytope and not just of each specific, and it's the same for all the triangulation for each polytope. So this encompasses huge class of compactifications for each polytope. So I like to refer to that as somehow universality of the standard model. So now we can analyze how many solutions do we have that satisfy tadpole conditions with 3 families of quarks and leptons. And that means that this combination of triple intersections with 3 families of quarks and leptons has to be positive integer number. And then we can turn to now toric constructions and see which polytopes have triple intersections that satisfy this condition. And it turned out to be this set of polytopes that have solutions is for this type of triple intersection. And this set of examples fall into toric construction. And now what we have to do is count how many of them we have that satisfy this condition. So we have around 4,000 reflexive polytopes and only around 700 satisfy this constraint. And now for each of these polytopes, we have to determine how many triangulations we have. And this is basically can be handled combinatorially, especially when the number of number of lattice points of polytopes is rather small. We can combinatorially determine for polytopes with less than 15 lattice points. We get that many standard models, but going beyond, for more complex polytopes, we had to turn to the computer and actually the way we estimate the number of all triangulation is to count this fine regular triangulations on facets and then estimate the number of fine regular triangulations for the whole 3D polytope using techniques developed by Jim Halverson and Tian. Anyway, this gives us at the end the full estimate of models that satisfy constraints for 3 family and tadpole conditions, and it's in the range of the quadrillion models. Okay. So this basically concludes the key results of these constructions. Let me just summarize again. This example of hyper surface constraint in F11 polytope produced for us actually generically just standard model construction that led to first family example, and now with this a scan of the toric basis led to the whole landscape of constructions on the order of quadrillion model. And one thing again I want to emphasize, those are all models that have natural gauge coupling unification. Okay, right. So now, yes, how much more time do I have? 15?
No, you have a more, 25 or more. Well, let me just ask,
Yes,
are there 15 or 16 bio spinors fermions in one family of standard model in your setup? 15 or 16?
They are 15. So right-handed neutrinos, okay, would come possibly from a complex structure moduli in the construction. This is some phenomenon that one often sees too, yeah.
Okay, thank you.
Yeah. So, and of course there are issues at the level of couplings and all that, but yeah. So I emphasize the good things and thank you for bringing up the issue of right-handed neutrinos.
But whether this additional maybe baryon minus lepton type of a symmetry.
Yeah, question.
Yes, the B minus L. can you remind me? I think that contains part of the Z2 as fermion parity, but other than that, does that has additional constraint in your theory?
Right. So you're referring to baryon violating couplings, okay? Because in passing, I was mentioning that one can construct models that have a gauge Z2 parity in themselves. This construction does not have manifest Z2 gauge symmetry. So the baryon number violation couplings are in principle there. So the actual magnitude of those couplings will be related to where we sit in the complex structure compactification of these fourfolds. So we would have to tune the complex structure to make the baryon violating couplings so small that to prevent, right, to be compatible with experiments. We believe that the fact that these models come from Patti Salam, they are unhiggsed version, namely as we change complex structure compactification, at some point we'll reach a point in this compactification where the symmetry enhances to the Patti Salam model, okay, which by itself may have some protection for us as far as this baryon violating couplings go. But this is an important phenomenological question that you raised, and these models, because they don't have a priori explicit Z2 parity symmetry, okay, may not be generically protected from this R parity violating couplings. Have I answered your question?
Kind of. So you will discuss Patti Salam.
Yes.
And the B minus L is sitting along the center Z fold of the SU fold of the Patti Salam? At least it contains part of it.
Yes.
Yes. Okay.
Indeed. Yeah. But this requires further investigation. Yes. And yeah, other issues also with the matter spectrum of the Patti Salam, how to connect it, right, through Higgsing or through deformations, and what couplings survive indeed in these standard models themselves. But a priori, one does not have discrete symmetry protection. There could be remnants from Patti Salam that are still there at the level of couplings of this standard model constructions. Okay.
Great. I'm interested in knowing if I have a B minus L preserved or broken or not there, does it make difference for your model?
Yes. Indeed. So if I had, yes, the features of the model depend on what its ties are, right, to this parity symmetry or U1B minus L. I mentioned in passing that we do have three family construction with manifest Z2 symmetry, and that's the one, actually you can trace it in geometry back to U1B minus L there. The thing is that in that case, we just were not able to systematically scan, right, all this landscape of models there. And the starting example that was rather for the rather simple base also didn't have gauge complex unification, and that's something we would like to probably, yeah, it's sort of appealing to have it.
Thank you.
Mm-hmm. All right, thanks. So now further analysis. So now I will I have 15 minutes or so, 20 minutes. So let me highlight more recent progress also. One issue is to address moduli stabilization with focusing on this big class of standard model constructions. And we know that that's an important issue. It's also related to issues of supersymmetry breaking. It has cosmological implications, dark matter candidates, right-handed neutrino candidates, and so on. So moduli stabilization was looked at recently for the example of these quadrillion standard models. And what we set out to do is to check under which condition would modular stabilization follow the standard effective field theory route with supergravity fluxes and having just perturbative aspects of string theory included, namely suppressing instanton contributions. So those are typical constructions that were used in our community that go under the name of KKLT or large volume scenarios. So in our context, what we are dealing with is with the gauge coupling. It's unified at the compactification scale, and it's related to the volume of the anticanonical divisor. And so this the running of gauge couplings from low energy to high energies produces for us the constraint that at the compactification scale, this coupling is, at least alpha is about 1/4. This in turn forces us, once we take string units to be 1, the volume of this anticanonical divisor to be below order of 100 in string units. So, so that's matching to the gauge coupling. The second one is we want all the divisors and curves to have volumes bigger than 1 in string units in order to suppress any kind of bullshit or the instanton contributions, right? Because this effective field theory and perturbative approaches would fail us. So this is like very strong constraint because those are most of the times techniques that people are using in modular stabilization, okay? So to study how often we get models that satisfy this particular constraint, we have to go to the so-called stretch killer cone for this constructions. Namely, we choose only choices of this construction that have the properties in the stretch killer cone where all divisors and all the curves have volumes bigger than 1. Now, the generic problem in our example is that we have the gauge group divisors to be parameterized by anticanonical divisor that is basically a sum of all the divisors in the construction. And so if all the divisors have to be large, then anticanonical volume divisor is typically expected to be large, okay? So we study distribution of the minimum volumes of anticanonical divisors in this stretch killer cone. And actually we didn't do all the triangulations, but 1 per polytope to see the distribution of the volumes of these anticanonical divisors. And we see that the number of these volumes is peaked around 10 to the 3. Okay, that is not suitable for the gauge coupling match typically. And the bigger the killer class, the more H11 for this construction is, the more examples we have. Okay. Now what we want to fit is in these examples is target the volume of anticanonical divisors that is around 25. Okay. So this tells you this excludes large number of constructions with large H11. And so if we say this typically allows us to look only at compactification with H11 less than 7 or so, maybe there's some freedom, but nevertheless, then in these classes, then we test how many triangulations we have for all these examples. And then we see that actually out of quadrillion models, we have reduced these conditions to be only satisfied for 10 to the 4th models, 10 to the 4th, maybe 10 to the 5 if I stretch it, okay? So this is huge reduction of allowed standard standard modular stabilization scenarios in these big classes of constructions. So what one could say is, yes, okay, 10 to the 4, 10 to the 5 is still a big number, actually as big as other constructions in other corners of string theory that have not even looked at things at this level. Or one could say that modular stabilization could take place in a regime where effective theory or perturbative string theory approaches fail. Of course, those are much harder things to address, and they were studied only in more specialized cases. And so the really application and real exploration in this domain for that type of models is difficult. Okay. Well, another thing would be, okay, maybe we can abandon this party line of having only standard model and gauge coupling unification. Well, that would then lead us to choosing different type of divisors, even in this classes of constructions. If we choose different divisors for the standard model, we were able to show that typically through geometric conditions forces us to have additional gauge group sectors beyond the standard model. Now, you can view that as a good thing or as a bad thing. I don't like it so much, but Jim and my collaborators do, and they think there is potentially very interesting dark sector implications in this regime. Okay. All in all, you know, this first delving into moduli stabilization really brings out the further issues in constructions of this model, and also is asking for further exploration of other standard model constructions. Even also in the context, I would say, you know, of parity, Z2 parity examples and so. So there is still a lot to explore in that context. Last but not least is now trying to address the issue of the complete matter spectrum in these compactifications. Not only namely the chiral spectrum, but also the vector pairs, okay? And this turns out to be a very difficult issue because it's not topological like chiral index, and really involves more detailed information on C3 potential that whose field strength may remain the same, but it can involve additional large gauge transformations that could, as we move in the choice of C3 potential, we can change the number of vector pairs. And this information on C3 potential is typically encoded in what one calls intermediate Jacobian of the Calabi-Yau fourfold. The net effect actually of that type of C3 potential has to be reduced how it affects meta curves, okay? So the C3 potential at the end has to be, the way it's in the full construction, has to be pulled back to the curve, the meta curve, where we want to calculate how many vector pairs and what its chiral index is. So as when pulled back on the curve, the C3 defines a specific line bundle on the curve. Okay. So to determine what is the actual exact matter spectrum associated with this meta curve, this would involve now calculation of a zeroth cohomology, namely number of sections associated with this line bundle on a curve, and H1 cohomologies. Okay, and then H0 would tell us how many massless chiral modes we have, and then H1 will tell us how many anti-chiral massless modes we had, with, of course, chiral index being topological invariance. Okay, and so the computation of this cohomologies, H0 and H1 cohomologies on the curve has been implemented via algorithmic procedures in computer algebra system that Martin Bies is heavily involved in. And but the really hard and difficult part is to really deduce the data associated with the line bundle from the embedding in the full Calabi-Yau of this three-form potential in the full Calabi-Yau fourfold. So that's very technically difficult. And that's the reason why for quadrillion models, we have not made much progress yet, because the construction is still rather complex, okay? And the genera of meta curves are very large typically. Well, the main goal for these quadrillion models would be if we could at least qualitatively or preferably quantitatively determine the range of complex structure moduli of this F-theory compactification, for which we would only have a minimal supersymmetric standard model. Namely, we would have to determine that we have only one Higgs doublet pair and no other vector pair exotics. And yeah, there's, of course, it's well-defined problem, but technically very involved because of the complexity of these constructions. Well, we are working on it, but really in the last few minutes, what I would like to report that we have made progress. You know, when we cannot do the real stuff, we simplify the problem where we could make more analytic progress, concrete analytic progress. And that led us to a major collaboration for which we have addressed analytic counting of vector meta pairs for a toy model, where meta curves were special. They turned out to be just hyperplane constraints of DP3, which specifies actually SU5 divisor. And then the line bundles are direct pullbacks of bundles that we find on DP3, namely where SU5 sits. And with this simplification, we can actually proceed with explicit and analytic study of how the cohomology of line bundle changes as we change the complex structure of this compactification or the complex parameter of the curves. Okay? And this can be done really rather explicitly. And we can encounter and study now origin of cohomology jumps in the case where this meta curve, which is hyperplane constrained in DP3, is just a smooth curve of genus G. Okay. In this case, we can determine the allowed values of H0 cohomology via Brühl-Noether theory. Namely, we involve the line bundle of certain degree D, look at its embed it then via Jacobi map onto the curve, Jacobi curve, and for particular degree of the line bundle, we get the number of 0 sections on the line, and also we can determine the actual dimension of this map. And the Brühl-Noether theory then tells us that there's degree, when this specific degree that specifies the dimension of this map is positive, namely it's so when the dimension of the map is positive, then this Brühl-Noether coefficient turns out to be parameterized by the genus of the curve, the number of sections, and the actual degree of the line bundle. And when this Brühl-Noether parameter is positive, then we know that this curve does contain degree D line bundle that has H0 equal to N. So this gives us a quantitative way to determine different strata of smooth curve that would at the end give us upper bound on allowed H0s. And we can also study when H0 jumps, but it cannot jump anymore once this number is smaller than 0. So this was one approach that was brought to us, because in the case of this construction, we can very explicitly study when Brühl-Noether jumps do happen in the conics, how we reach different strata of line associated with line bundles. But there was another phenomenon that we also observed, that now this curve can split into components, and often this extra component that peels off from the original curve is it's a rigid curve typically. And in this case, when we are looking at split components, we are dealing actually with a singular appearance of singular meta curves. And the splitting generically leads to jumps in cohomology as well. And one can actually develop also algorithm to count those jumps by a computer. And what I want to show you is an example of genus 3 curve with degree 3 line bundle corresponding to chirality 1. That was a generic curve, H0 was 1. Then we were able to reach a stratum of by a Brill-Nutter procedure, where this curve is regular, but now the H0 has jumped by 1. In addition, we see now splitting of curve, original curve, when one rigid curve peels off or another rigid curve peels off, all related to rigid divisors of DP3. And then there is another jump to 3, where actually we see the peeling of 2 rigid curves from here below, both of them at the same time. Okay? And so this, we like to talk this stratification diagram, which we can actually explicitly quantify also in terms of parameters of the curve. We know precisely for what parameters of the curve we have Brill-Nutter jump, and for what parameters of the curve we have the corresponding rigid curve peeling off jumps. And furthermore, we could explore this study on large number of examples in this case, and actually so many that we could also reach certain complementary results from machine learning algorithms that we also implemented, but I don't have much to say about it. So this is just, you know, a first venture into trying to understand jumps in cohomology and how it depends on changes of the complex structure and what kind of jumps we can get either through singular geometry or also implementing a Brill-Nutter theory. Of course, in a real context of standard model with complexities I was alluded to, this is much harder thing and much harder to address systematically. The example we chose is the one that we could really systematically and completely address and study. In any way, I think that brought me to the end of my lecture. So what I tried to give you is an overview of a broad program to extract particle physics feature from F-theory compactification. And I hope I have given you the impression that we have come a long way, but also giving you the impression that there is so much more to do and to explore. And what I foresee and what I'm actually quite involved in is also advancing technical aspects of constructions. In particular, I think as a matter of technical achievement, I think it would be great to find the exact matrix spectrum or having enough control over the exact matrix spectrum of this quadrillion standard models and pinpoint regimes in the compactification where we get indeed minimal supersymmetric standard model 1. The thing that I have not mentioned at all is Yukawa couplings. This is also very hard and difficult problem, especially in compact constructions. And while really at this point, impossible, hard if not impossible to address in terms of this standard models, we have made progress on that on compact toy type models, again, SU5 plus U1 type models using spectral cover constructions, but I have no time to that. This is another big technical problem in really compact spaces. And as alluded through questions raised, also through exploration of our modularized stabilization scenario, it's important to address other particle physics models and possibly saying some general statements beyond toric techniques that we have primarily explored in our context. So another direction that I foresee as very intriguing and important, and we stumbled over that already within our specific constructions, is that F-theory that as a geometric framework could be extremely useful for addressing specific swampland constraints, like global gauge group constraint that we saw was encoded in the presence of U1, right, in the Shioda map, or other conditions related to other type of symmetries. For example, one-form symmetries could provide extremely fruitful framework to quantify those specific constraints. And here I'm advertising a paper with my collaborators that is just about to appear, and I believe would be a focal part also of Link's talk tomorrow. Thank you.
Thank you, Professor Mirjam Cvetic, for the great lecture. Any question from the audience?
It felt a little bit isolated for me and very long winding, so I hope you didn't have, all of you, that feeling.
Good talk. Nice work.
I have a question, Mirjam. So very nice talk. So I have a general question about how do we use these insights to learn something about the standard model, and what's the perspective on it in the following sense. So the global structure is one thing, which is of the gauge group and so forth, which come. The matter content is another. The connection with the grand unification story is the other. So all of these in the approach that you were following were put as input rather than as a consequence. In other words, you were not interested necessarily in how the grand unification is part of it or not, but you said if you wanted, you could do this or that. But it was in some sense not necessarily natural to insist on it. So, but the fact that we know that in our models we do have some kind of grand unification, I mean, that's probably very reasonable to say that we do have. So the question is, how do you reconcile your constructions? In other words, just to go back to a more specific case, for example, in your F11 models that you were talking about, those models came from fibration on F11, with the fiber being F11, and those naturally have, from the 60 perspective, an E8 times E8 with instantons distributed as 23 and 1 between the two E8 factors. So naively, one E8 is broken and the other E8 is basically there. So I'm wondering, for example, is that the reason that you're getting in those models, when you fiber these models over an extra base, you presumably break this other E8 further down to get your standard model? Is that what's going on? So, I mean, I just want to have a better geometrical handle about what it is that is leading to these unifications. And are there any extra information that you're getting within the classes that have the standard model structure? What is the unifying feature of the geometry? What features do geometries have common, other than the fact that they just produce this particle spectrum?
Right. You know, I cannot probably answer this very sharply, but some things that are sort of clean, you know, we can take other fibrations, right, but would not generically get these gauge group factors popping out for free. Namely, we would re-specialize coefficients. I think what is somewhat intriguing, and I don't have deeper answer to that, though you're alluding to this E8 cross E8 origin. These gauge group factors come there without specializing fibration anymore.
Right.
It's sort of encoded in there. Another data point I want to mention that Taylor and Andrew Turner, in their analysis of a spectrum, they did 6D analysis originally, right? But they looked at the Weierstrass fibrations that would produce just the standard model and particle spectrum of the standard model, no exotics. That led them uniquely to this specific fibration, right? So this is alluding that there is something very special in this specific fibration, though it was stumbled upon, right, as more phenomenological, bottom-up thing to get a standard model. So I'm not answering your question sharply because I don't have definite answer, but there is something magic in this particular vibration as far as the symmetry groups go. Okay.
And do you have different global structures in your standard model?
A global, for this construction, right, it uniquely came out from geometry that is Z6.
No, I mean, what I meant is that if you just insist only on the standard model spectrum,
yes,
in principle, you could have had different global symmetries?
You mean a different modding out by discrete, different discrete?
Right.
Yeah,
right.
in principle you would, but then the spectrum, but then that would typically also produce probably some exotic stuff.
Well, yes, it could be massive exotic stuff, for example. My question is whether or not your models necessarily say if you have this model, then the modding out is always Z6 or whatnot. In other words, what is it that does your model predict? Does the F-theory geometry predict that, or is it some input?
It's F-theory predicts that. It's the Shioda map for the U1 in this construction that forces it to be Z6.
Okay, so you're making a prediction, therefore, from geometry that this has to be the case.
Precisely from this geometry, yes, yes. That is sort of a neat thing, I think, in this context, because the Shioda map is completely geometric statement. It's all intersections with Cartan divisors that determine coefficients that tell you it's Z6. Global
So
thing.
can you recover that from some swampland condition without going through the construction? In other words, what is the, is that related to, for example, cobordism triviality or whatnot? Can you relate that to some other principle? You're saying that from geometry, you're always seeing this Z6 modding out.
Yes, yeah, yeah. This was directly found really from geometric perspective in F-theory. I don't have a big, again, I'm not, you're asking very important questions for which I don't have clear answer. I have just empirical evidence what was obtained in this context, but it's clearly should fit in a better and bigger understanding.
Thank you.
Mm-hmm. Thank you. Ling, do you have maybe any other comment on that?
Yeah, so regarding the general swampland considerations, I think we have thought in that direction a little bit, and what it comes down to is that we're kind of missing a component in a key argument that I think essentially relates to, in some sense, how I can read off from the massless spectrum, or if I can read off from the massless spectrum, the charge, but the normalization of the U1 charges.
Right.
And of course, naively, that should not be possible because there is no reason why just a massless spectrum would tell you that. If you think about 60, the examples, for example, that were studied from the perspective of the weak gravity conjecture by Timo and Wolfgang and Sonju, there it seems to suggest that if you include string states that are naturally there in the theory, then that should fix for you, in some sense, the lattice spacing of your charge lattice. And if you combine that with the arguments that we had in this paper that Mirjam was also referencing to, and which I'll cover to some extent tomorrow as well, I think you could, in some sense, prove that or argue rigorously that the Z6 quotient has to be there.
Okay, thank you.
But yeah, it's a bit of a stretch in that I don't know how to make that one key argument precise.
That's what I like to refer to. We need a measure stick, right?
Indeed.
Yeah, we need a measure stick that you have to expect, yeah, to have something that measures and sets for you what is the charge of U1, right? Anyway, I'm sure you'll have a chance to say more about it tomorrow. In connection with with Kumrun's comment, we do find other examples of standard models, like with Z2 parity, right, which is becomes a real Z2 gate symmetry, right? Also to go back to questions raised, right? And it's intriguing. String F-theory knows the right parity that you have to implement that is anomaly free and all that. And it is a descendant, geometric descendant of the model with U1B minus L, okay? But I do want to say there you see the vibration that we chose. We had to specialize coefficients. It's not like broad strokes answer, right? With special coefficients to produce that. So it's more specialized domain of constructions as well, and more, you know.
Well, I should comment that it's related to also what commented earlier about the Yate instantances, that the F11 model, sure, the way you represent the elliptic fibration in terms of a hypersurface inside F11 is a generic hypersurface, but that doesn't actually mean it's in a generic elliptic fibration with certain features, right? So if you write down the Weierstrass model for the F11 model, then you have enough complex structure to tune around that can get rid of all the standard model gauge groups, for example. So it's in some sense a generic hypersurface in F11 because you've chosen to embed your elliptic fiber already in a particular fiber ambient space. That doesn't mean, of course, that what I said earlier and also what you alluded to earlier, Kongan, about maybe there is some unifying feature behind saying requiring certain representations to be present and others to be absent that maybe end up on this kind of model, and maybe Watti's work is pointing towards that direction. I don't really, yeah, I can't make a rigorous statement about that.
Right, yeah, I wish, yeah, if they were here, they could have commented probably more on that point, yeah.
Yes. One more question I have, actually, somewhat related maybe to the comment you made in your talk, but maybe not. But so one thing about the standard model is that it has many different unification scenarios, like Patti-Salam model, the Georgia-Glashow model, and this and that. And they're kind of related, but they're kind of disjoint in some way. Sometimes they come together. It's like a tree structure. Now, this reminds me of in string theory, for example, when you have Narayan moduli space, you can have isolated points with gauge groups which don't fit with each other. Like you can have one gauge group here, you change the moduli, you get a different gauge group there, and there is no global gauge group which includes both of them. And we might have thought if from effective field theory, if somebody told you both of them are consistent with your theory, you would say, no, that's wrong. One or the other is correct. But we know that does arise in string theory. So my question to you is that in the context of these F-theory models, since you have only taken the common ingredient, which is the standard model, SU3 cross SU2 cross U1 model, is it possible that in your models, a single model incorporates different grand unification, quote unquote, schemes as different points on the moduli, even though these moduli are somehow masked up or somehow are not allowed variations from your constructions? But if you were to somehow try to make a notion out of it as if you were going to change moduli, even though they're somehow masked up, if you go away from zero energy locus, could you find these isolated or these other kinds of grand unification schemes which would have fit? So in some sense, trying to bring the picture of grand unification as a more basic ingredient in these geometric models, which is not possible in particle physics perspective, but from stringy perspective, it comes to life.
That's a very good point, and I alluded to this a little bit. If I'm sticking just to toric basis, you know, I can do that and reach Patti-Salam, okay, geometrically. So that's one direction in the complex structure deformations. Okay.
And SU5 in the other direction.
Yeah, and that's non-toric, and that's the one found by.
So you
right?
could, in some sense, do realize this idea. That's what I thought you said. I was just trying to make sure I understand. So you're, in some sense, you're saying that string theory realizes this, this possibility that both models arise consistently in a single framework.
So in a bigger context, I go beyond, right? Toric, I can reach both.
I mean, as far as they're my question is whether they're connected in a given geometry.
Yeah.
So you can have transitions from one geometry to another, as long as there's they're finite distance apart or somewhere in some sense nearby.
Well, the way I would see it, you know, you see Patti-Salam there sitting, right? You go via this route of standard model, then you go in the non-toric direction, you go into SU5. So now you're asking, is this Patti-Salam, how is it related to SU5?
Yeah.
I really have to go through standard model, right? Or what is the bigger moduli space through which I'm connecting, right? This different tree of guys. Clearly, I would say that, you know, it's worth studying and understanding how these connections fit, right? Because we have enough knowledge of the geometry part at this point.
Yeah, that sounds fascinating. I think it's, especially from the particle physicist viewpoint,
yes.
This is, I think, it should be brought out to them that they are could both be consistent without contradicting. It's not an illogical statement to say both are correct.
Right.
Or
Indeed.
both could be correct. Okay, thanks.
I have to say that I often get this question, you know, like Juan or others immediately ask, can you get SU5? That's the first thing one has asked me, right? Can you get SU5 from this, right? Is it there? Yeah, it's there, but in a hidden way, in a different way, okay? It is there. You can trace it. That's what, Matthew and Wati showed. And we start, okay, anyway, it's all in part of this bigger picture. Yeah, that's very interesting, points that we have to understand better. Yeah, thank you.
I have a question. Maybe people also have more.
Yes.
Thank you very much for nice lecture, Nadisha Hwada. And the question is, are there additional matter contents you can predict beyond standard model?
Mm-hmm.
Is there something more than just the standard model matter contents that you write down?
Well, in this route, okay, this route forced us for geometric consistency, the one we took with this vibration, forced us to have the matter spectrum, right, that fits into standard model matter spectrum only. Okay. In these constructions, we could also get vector pairs, like we could, in principle, we could get quark vector pairs, which we don't want from MSSM, okay? But we get no chiral exotics in the spirit of additional matter beyond the one in the standard model. In these constructions, I thought, you see, a little bit, if you say, you know, lowbrow, bottom-up approach, the fact that we could get the model that has no chiral exotics, right? Only the content of the standard model. It's an important assignment that string theories should answer. And when they are asked to do that, they get often models that have standard model plus stuff, okay? The fact that this particular construction filled up, you know, from the D7 brane perspective, the whole gauge group of the standard model, and that's it. No other ones coming from D7 PQ branes. Also, as a byproduct, gave us only the standard model matter. And again, yeah, that can be proven in general in this context. There are other constructions. Also, I would say I could go to some other constructions that could force us then to also have additional D7 PQ branes, right? D7 PQ branes, right? That would give us additional D7 spectrum. And then typically, maybe at least at the vector pairs, you could have matter that is charged under both sectors. And that often causes either people turn this around and they do intriguing dark matter phenomenology, right? Or you would say, okay, this is now complicating. This is complicating our standard model part, right? And you don't want it.
Maybe let me clarify. I think most of the time, particle physicists, they try to say the standard model matter content is some particle that can couple to one form gauge field.
Yes.
And possibly people study supersymmetry model, but again, those matter field will be some representation of some gauge group or some representation of something. It's a matter field, it's point particle in terms of Hilbert space realization. But
Yes.
my question is about, are there something beyond particles? Perhaps, you know, if you are familiar with like a TQFT, like Chern-Simons theory, they can have like line operators. If you go to higher dimensional TQFT, and that's natural if you start from a cobordism point of view, start from some cobordism invariant, given some space-time and internal structures group, and then you try to gauge this group, then it's natural to get a lot of topological theory. And certainly it doesn't have to have anything to do with standard model. But I was wondering, say, in your construction, whether there could be such input given the standard model matter content, are there still possibility to have additional matter which is not quite the particle matter contents that people familiar? Perhaps there could be extent objects. This sounds maybe foreign, but it's actually not a random question, because I think my recent pursuit, I think there's a possibility of such things can come naturally. And I was wondering, say, if you start from this particle physics input, the standard model matter content, are there still room for something beyond particle physics data?
Yes,
I don't know it's clear to you. I don't
have a definite answer to that, but I think Ling will touch upon some of the related ideas that come from one-form symmetries and possible effects.
I mean, I can't really say anything about in terms of 4D compactification, anything substantial.
Yeah,
but certainly these kind of extended objects that couple to some higher form symmetries are almost naturally there in string constructions, right? You have, in addition to these kind of 7-brane sectors in any compact model, also always some Ramon back C fields that are higher form fields, which have other charged objects under them. So in particular in 4D, you know, there can be also some strings which are not necessarily preserving the supersymmetry you want, but they will be there, and in fact also responsible for some saturation of weak gravity conjecture and other kinds of swamp blend considerations. I think in 4D it's very hard to analyze them in detail, but these kind of objects do appear in higher dimensions and will be in a will be there in addition to the 7-brane gauge sector.
Nice.
And actually play a crucial role.
But you're related to that question. In your examples, can't you look, for example, at the second homology and see if they have torsion elements in your constructions? And if so, they would correspond to strings which have discrete charge. Those kind of things you can, in principle, check in your constructions, right?
Yeah, but yeah, that's something that is
right.
Done much.
Right. So I think in our cases, since we looked at toric bases, mostly there won't be any torsional homology. So these kind of interesting objects probably won't be there in that
okay,
case.
well, if you have examples that they don't be there, then that means there's no argument for them to be there. If a single counter example is enough. In other words,
yeah, I guess if you include more general bases, then, and we know there are bases that can have certain torsional homology, then there should be examples. Although, as I said, I don't know exactly then how the couplings explicitly would look like to the standard model sector, and what kind of back reaction you could see from them.
Right.
Yeah.
So you're at an advantage in the sense that you can just check what kind of experimental data you're getting. You just input the matter structure you want, and just see what kind of exotic objects you get, and that you can easily, presumably, check. Not necessarily trivially, but at least you can, in principle, check what kind of matter you get, exotic stuff, in the form of, let's say, strings with discrete charge and this and that, which or domain walls or whatnot, that just simply follow from geometric construction itself. And if you get a general restriction, then you can say, oh, let me see what's the reason for this. And if you don't, then you say there is no restriction, and that already is an interesting state.
That's true. Yeah. Though, so I think since before you mentioned it, I haven't thought about in that direction, to be honest. I think, but I think there is, as you said, in principle, a lot of things that can be done and haven't been done yet in any level of detail. So probably there's a lot to find out if one just looks carefully enough in that direction.
Yeah, so, well, as Ling also points out, in higher dimensions, right? You have higher form fields there, they're part of topological coupling, Green-Schwarz coupling, other anomaly cancellation couplings that naturally lead to these higher form fields and objects associated with that. But yeah, we didn't think in 4D context as much about that. Yeah, indeed. Okay.
Actually, one more question. I'm not sure we'll fit into content, but thanks, Lynn, for the comment. That helps. I wonder, usually when people talk about topological theory, I'm not sure whether you will even have topological field theory in your setup, but suppose, let's just briefly talk about topological field theory. So usually people will say the Hamiltonian of TQ is zero, Hamiltonian zero. So nothing other than just, possibly some zero modes or ground state degeneracy that the dimensional Hilbert space may depend on topology of space-time manifold. And however, if you try to really go into deep UV, there could be some energy gap. That's the gap of TQFT energy gap. And usually at low energy, people don't worry about this, the gap and the qualities of both. Was one thing, say, since Lin is saying about this higher symmetry, I think that could have a room for topological field theory. I was wondering, say, is there some constraint one can give to this type of gap, the energy scale for that gap? I don't know whether this question is clear to you. For example, in the standard model, the particle contents, those matter fields that have a relatively small mass, but
they are at the scales at which we are looking at the spectrum, right?
Yeah, right. But if Lin say that there could be some possible higher form symmetry, then there should be corresponding charge objects, right? That's extend objects.
Yeah, that's what Kumran is referring to also.
Right. But I say that are there energy scales associated to them? For example, the line operator in three-dimensional TQFT, if you break up the line operator, there could be anyons, right? That's a point particle in the sense of the endpoint of line operator's anyons. But the anyon is relatively heavy as a gap, TQFT energy gap. In order to see those anyons, you need to create anyons, and that's the energy gap. The energy gap is, in the condensed matter sense, is a lattice scale energy. But in the quantum field theory sense, it's a really large energy gap. But in terms of fitting to the story, if you have a higher symmetry in your model that Lin will talk about, then there will be some extend objects. I was wondering, say, are there associated energy gap to open up those operators by, break up, like a line become open line with endpoints? So
yeah.
Is there some?
So, I mean, if I take the analogy from, or an intuition from, say, 6D, then the most common objects are strings, BPS strings, which in the F theory or type 2B realization come from D3 branes wrapping some curves in the base, right? So the natural scale you would associate to these to these objects and their excitations would be related to the volume of the holomorphic curve in the base that they wrap. So roughly speaking, I would have said that unless you have some, very contrived hierarchies, then these scales would typically be of the order of the KK, of the volume of the total compactification space in certain powers. So it should be around the KK scale, which, is from, in lower dimension would be, very high compared to anything that standard model or beyond the standard model phenomenology would observe, say, or be worried about. I don't know, that maybe that's not correct, but the rough estimation would put it there, I think.
I see. Yeah, I was thinking maybe could there be additional constraint? Those scale happen where, for example, maybe gas scale and which type of gas scale, or maybe lower or above, right? But I think you answered my question. Thank you. So, any more questions from the audience? Well, if not, let's thank Mirjam for the great lecture. Thank you very much. And tomorrow, at the same time, we have a LinkedIn tell us the second part of the talk, and please stay tuned. Thank you very much. Thank you.
Enjoyable. Thank you. Goodbye.
Bye-bye.
Bye.